This video is an introduction to improper integrals. This is a BC only topic. Improper integrals are set up like definite integrals, except they involve infinity. You can see the infinity here and here on the first two examples, but what makes these second two examples improper? For the one on the left, if x is equal to 1, then we have 1 minus 1 giving us a 0 in the denominator. That's why we see this vertical asymptote at x equals 1. We know that the integral is the area under this curve, but the area goes technically to infinity. The upper limit of integration is 10, so the area stops here on the right-hand side. But the lower limit of integration is 1. As x approaches 1, the curve, and thus the area, approaches infinity. So in this case, the lower limit of integration is the issue. For the last example, neither limit of integration is a problem, but we do see a vertical asymptote at x equals 0 because that causes the denominator to be 0. Because of the limits of integration, the area stops here and here. But because of the vertical asymptote, the area approaches infinity near the asymptote. The thing that's going to blow your mind is that just because the area approaches infinity doesn't mean that the area is actually infinite. Sometimes these areas actually approach a single number, all right? Sometimes even though the area approaches infinity, it actually works out to be a constant. And sometimes it does in fact approach infinity. An integral that looks like a definite integral is an improper integral if the lower limit is positive or negative infinity, and or the upper limit is positive or negative infinity, and or f of x is undefined on the interval from a to b. We have to be very careful about the vocabulary we use when we talk about the value of an improper integral. For example, we won't talk about infinity, we won't talk about what is undefined or what does not exist. Instead, the key words will be converge and diverge. An improper integral converges if the value of the integral is a real number. Let's say the value of the integral turns out to be c. We would say the integral converges to c. An improper integral diverges if the value of the integral is not a real number. For example, if the value of the integral is undefined or some kind of infinity, we would say the integral diverges. Here are the 3 steps we will follow to evaluate improper integrals. Step 1, we will define the antiderivative as capital F of x. Step 2, we will write 2 or more limits. And step 3, we will evaluate. What you're not going to do is use this definite integral notation with an infinity in there. If I see this on the test, or if they see this on the AP exam with an infinity with a vertical line as a limit of integration, the problem will be marked wrong. Example 1 is an improper integral because the upper limit of integration is infinity. The first step is to find the antiderivative of the integrand and call it capital F of x. We can find this antiderivative using a mental u substitution. If u equals negative x, then u prime is negative 1. We always end up dividing by u prime, so we need to divide by negative 1. That's why we will have a negative in the front. Then the antiderivative of e to the u is e to the u. Don't worry about the plus c. Next we set up 2 limits. First, the limit as x approaches the upper limit of integration, and second, the limit as x approaches the lower limit of integration. First, let's find the limit of f as x approaches infinity. You should be able to do this in your head. I'm going to show you my thought process using some bad notation. Do not write this on your test. If you do need to write something down, write it on scratch paper. Since x is approaching infinity, we have negative e to the negative infinity. The negative exponent drops this expression down to the denominator, so this would be the same as negative 1 divided by e to the infinity, which would be the same thing as negative 1 over infinity. In other words, we have negative 1 and the denominator is getting bigger and bigger and bigger. So the limit is 0. We can find the second limit by direct substitution. We have negative e to the 0 power. E to the 0 is 1, so this is negative 1. You know how we usually evaluate a definite integral by finding the value of the antiderivative at the upper limit and subtracting the value at the lower limit. We are going to do something very similar now. We will take the value of the upper limit and subtract the value of the lower limit. We do 0 minus negative 1, which is positive 1. Using our vocabulary, we say the integral converges to 1. Let's take a look at this same problem graphically. As x approaches infinity, e to the negative x gets closer and closer to the x-axis, but never touches. So this yellow area gets thinner and thinner, but never becomes 0. This can be kind of hard to wrap your head around. Even though the region is infinite, the area is not infinite. On the previous example, we found that the area is exactly 1. Here's another example of an infinite region that has a finite area. We start with this square, 1 by 1. Of course, the area is equal to 1. That's not the infinite part. Let's start by taking half of this square. So the area is 1/2 so far. Then we add in half of the remaining space. So that's 1/2 plus 1/4. Again, we add on half of the remaining space. So plus 1/8. If we add half of the remaining space again, we are adding 1/16. You can imagine adding half of the remaining space over and over again forever. As you do this, we are getting closer and closer to filling in the square, but we never quite finish. Even though this pattern is infinite, we say that the area is equal to 1. Or, in both examples, we could say that the area converges to 1. Example 2 is clearly an improper integral because the lower limit is negative infinity. Step 1 is to find the antiderivative of the integrand and call it capital F of x. And this is just a memorized rule. We know that the antiderivative of this is arctangent. Next, we need to find the limit as x approaches 1 and the limit as x approaches negative infinity. The limit as x approaches 1 can be found by direct substitution. The value of arctangent 1 is the answer to the question, the tangent of what angle is equal to 1. The tangent of pi over 4 is equal to 1, so that's the limit. Finding the limit as x approaches negative infinity is not going to be so easy. First of all, the value of arctangent x is the answer to the question, the tangent of what angle is equal to x. If tangent is equal to x and x is approaching negative infinity, that means tangent is approaching negative infinity. This in turn means that sine over cosine is approaching negative infinity. If we want the value of this fraction to approach some kind of infinity, it would be helpful if cosine is approaching 0. If you're dividing by a really small number, the value of the fraction will get larger and larger in absolute value. If we want the value to be negative infinity, it would be helpful if sine, the numerator, was negative. On the unit circle, cosine is an x value and sine is a y value. So where is cosine 0? Here and here. In which of these positions will the sine function be negative? Only here. Let's call this negative pi over 2 instead of 3 pi over 2 because arctangent is only defined between negative pi over 2 and positive pi over 2. As we approach negative pi over 2, cosine is getting closer and closer to 0, while the sine function is approaching negative 1. As the denominator gets smaller and smaller, the magnitude of this fraction gets bigger and bigger. But are we approaching positive infinity or negative infinity, which is what we actually want? Well, the sine function is approaching negative 1, so the numerator is negative. Cosine is approaching 0, but it's approaching 0 from the right. We are always on the right-hand side of the unit circle where the x values are positive. Since a negative divided by a positive is a negative, we are approaching negative infinity. So, approaching what angle causes tangent to approach negative infinity? Negative pi over 2 is the angle we are looking for. So that's the limit. By the way, if you are familiar with the graphs of tangent and arctangent, there's an easier way to find this limit. I've drawn the portion of the tangent graph between negative pi over 2 and positive pi over 2 because arctangent is only defined between these two values. Reflecting the tangent graph over the diagonal line y equals x gives us the graph of arctangent. So if we want to know what the limit of arctangent is as x approaches negative infinity, we can just use the graph. As we go to the left, arctangent gets closer and closer to negative pi over 2. So that's the limit. We can find the value of this improper integral by subtracting the upper limit minus the lower limit. In other words, pi over 4 minus negative pi over 2. So here are three versions of the final answer. In order to find the antiderivative for example 3, we first must rewrite the integrand. We can find the antiderivative by u substitution if we let u equal negative x squared, in which case u prime will equal negative 2x. As we do the substitution, we take away the limits of integration for now, and we have this. Instead of writing dx, we write du over u prime, so du over negative 2x. But the x's cancel out, and we will bring the negative 2 out to the front as a negative 1/2. Let's call the antiderivative capital F of x. We keep the negative 1/2 in the front, and the antiderivative of e to the u is still e to the u. We can get rid of the negative exponent by writing the antiderivative as negative 1 over 2e to the x squared. Next, we need to find the limit as x approaches positive infinity and the limit as x approaches negative infinity. Don't write this part in blue on your paper because this is not proper notation. I'm just showing you my thought process. As x approaches positive infinity, we have e to the infinity. In other words, this denominator is getting bigger and bigger and bigger. Therefore, the value of the fraction is approaching 0. What if x is approaching negative infinity? Well, x is being squared, so a negative number will become positive, and we are right back to this. So this limit is also equal to 0. For the final answer, we subtract the upper limit minus the lower limit, and of course 0 minus 0 is 0. Or if we wanted to use our words, we could say the integral converges to 0. A glance at the graph of the integrand reveals why the integral converges to 0. Because of the symmetry of the graph, from negative infinity to positive infinity, we have equal and opposite area between the curve and the x-axis. So the negative area below the x-axis on the left will cancel out the positive area above the x-axis on the right, giving us 0. For example 4, we do not see infinity for the limits of integration, but this is still an improper integral because we have a vertical asymptote when x is equal to 1. 1 minus 1 is 0. Dividing by 0 gives you a vertical asymptote. We can rewrite the integrand like this. We can now find the integral using mental u substitution. U is x minus 1, so u prime is 1. We always have to divide by u prime, but dividing by 1 changes nothing. So we can just use the power rule of integration. So here we have u, and we increase the exponent by 1. So that gives us positive 1/2. Then we have to divide by the new exponent, but dividing by 1/2 is the same as multiplying by 2. So here's your antiderivative. The antiderivative can be written like this, and we can find this limit by direct substitution. So we have 2 times the square root of 10 minus 1. That's 2 times the square root of 9, which is 2 times 3, which is 6. Similarly, the limit as x approaches 1 is 2 times the square root of 1 minus 1. That's 2 times the square root of 0, which is 0. The value of the improper integral is the upper limit minus the lower limit. So the final answer is 6. In other words, we could say that the integral converges to 6. In example 5, if we allow x to be 0, we are dividing by 0. So we have a vertical asymptote at x equals 0. That's within the interval between -1 and 2. That's why this is an improper integral. We can rewrite this integrand as x to the -2 power. Then we can find the antiderivative, which we will call capital F of x, using the power rule of integration. Adding 1 to this exponent gives us x to the -1 power. Then we divide by the new exponent, which gives us a negative in the front. Another form of this antiderivative would be -1 over x. When you have a vertical asymptote that is between the limits of integration, you have to split the integral at the asymptote. So we have one integral from -1 to 0, and then another integral from 0 to 2. Because we have two separate integrals, we potentially have to find 3 different limits. I'm saying 3 and not 4 because the limit as x approaches 0 is repeated. Let's take them one at a time. As x approaches 0, the denominator is getting smaller and smaller and smaller, so the magnitude of this fraction is getting bigger and bigger and bigger. It's approaching negative infinity. We can say that the limit does not exist. No need to find the other 2 limits. If even one of the limits does not exist, the integral diverges. Note that this is the answer, not dne or negative infinity. The final example is a little bit more involved. We start by rewriting the integrand like this. If we try to do u substitution, it doesn't work because if u is -x, then u prime is -1. Dividing by -1 will not cancel out this x, so we're stuck. Only we're not really stuck, we just have to use integration by parts. We have to decide which part of this expression will be u and which part will be v. Let's start by choosing the best u according to the acronym LIATE. We see that we have an algebraic factor, x is a tiny polynomial, and an exponential factor. According to LIATE, algebraic is better for u than exponential. So let's let u equal x. Earlier I said we had to find u and v. It's really u and dv. And since u is x, that means dv must be e to the negative x dx. Taking the derivative of both sides gives us du dx is equal to 1, but we really want du by itself, so let's multiply both sides by dx. So du is equal to dx. We can find v by taking the antiderivative of both sides. We can do this using a mental u substitution. If u equals negative x, then u prime is negative 1. We always have to divide by u prime. Dividing by negative 1 leaves a negative in the front. Then the antiderivative of e to the u is still e to the u. Next, we set up the right-hand side of the integration by parts formula, starting with u times v. That's this times this. Next, we have minus the integral of v du. That's this times this. The negative sign on this e is going to come out to the front and turn this minus to a plus. This small integral is the same as the integral we did when we found v. So we are doing a mental u sub, u is negative x, so u prime is negative 1. We divide by u prime, which is why there will be a negative in the front. And then the antiderivative of e to the u is still e to the u. So this is the antiderivative of the integrand, which we will call capital F of x. Factoring out the common factor of e to the negative x, we have this. I think it will be easier to work with if we drop this e to the negative x down to the denominator and make it e to the positive x. Next, we need to find the limit as x approaches infinity and the limit as x approaches 1. As x approaches infinity, the numerator approaches negative infinity and the denominator approaches positive infinity. We can use the acronym FEPL to help us decide which infinity is growing faster. FEPL ranks the different types of expressions in order from fastest to slowest growing. In the numerator, we have a polynomial, and in the denominator, we have an exponential expression. Exponential expressions grow faster than polynomial expressions. Since the denominator is growing faster than the numerator, that means the denominator is getting bigger and bigger and bigger compared to the numerator. So the overall value of the fraction is getting smaller and smaller and smaller. In other words, the limit as x approaches infinity is 0. Alternatively, since the numerator and the denominator are both approaching infinity, we could use L'Hopital's rule, which says that we can take the derivative of the numerator and the denominator without changing the limit. So in this case, the derivative of the numerator is negative 1, and the derivative of e to the x is still e to the x. So the limit of this expression is the same as the limit of capital F of x. Either way, we see that the denominator is getting bigger and bigger as x approaches infinity, while the numerator remains small. So the value of this expression approaches 0. So either way, the limit is 0. We can find the limit as x approaches 1 by direct substitution. Substituting 1 for x, we have negative 1 minus 1 over e to the 1, or just e. That gives us negative 2 over e. The value of the improper integral is the upper limit minus the lower limit, so 0 minus negative 2 over e, which equals 2 over e.